everyone. Thank you for coming today. I'm Idahen님, PhD of Yonsei University College of Medicine. Before we start, I really appreciate for giving me this opportunity and choosing me as the winner for this award. I'd like to introduce one of my publications, Physics to Activate NRF via uricane-mediated autophagic carbon degradation and protect mouse liver from lipotoxicity. Firstly, I want to start with an overview of my research. Non-alcoholic fatty liver disease is a spectrum disease ranging from simple steatosis to non-alcoholic steatohepatitis, called NASH. NAFLD is the most common chronic liver disease that is associated with various metabolic disease such as obesity and type 2 diabetes. And it can be also developed into cirrhosis or liver cancer. However, up to now, there are no approved drugs for NAFLD treatment. The progression of NAFLD can be explained by two hit theories. The first hit is when repeats in the increases in the normal liver, and second hit is when ROS, ER stress, and inflammation increase in the fatty liver. These additional factors lead to NASH progression. When fatty acids are overloaded in the liver, this can induce ROS generation. It causes oxidative stress-mediated cell death, also known as lipotoxicity. It is most crucial pathogenic factor in NAFLD. To eliminate intracellular ROS, there is a carbon NR pathway that has a cellular antioxidant function. Also, autophagy has many beneficial functions to prevent NAFLD. This self-degradation pathway works by removing organelles or protein aggregates or lipids under nutrient stress through maintaining essential cellular metabolism. Based on this overview, I hypothesized that regulator for autophagy ROS axis can be a good target to find NAFLD. So who can be the best regulator in lipotoxicity? P6 is one of the answers. P6 is an autophagy receptor protein and also known as NR target gene and potential biomarker of NAFLD. However, the role of P6 in lipotoxicity remains unclear. So it makes me wonder, can P6 protect cells against lipotoxicity? To set the in vitro approach for NAFLD model, I used the treatment with fatty acids, thereby inducing lipotoxicity in hepatocytes. As you can see from the outcome of my research, I found out that P6 rescue decreases cell death marker through NRF activation followed by decreasing ROS. Therefore, P6 is required for cytoprotection against lipotoxicity. Consistent with previous reports, I was able to confirm that P6 is accumulated in response to palmitic acid. In addition, P6 induction is mainly dependent on ROS NRF axis in lipotoxicity. And the new question emerged, can P6 regulate autophagy? I used GFP-RC3 HeLa cells to clarify whether P6 activates autophagy. Look at the panel H and J. Infection of adenoviral P6 significantly induces the reverse of GFP-PONTA and GFP-RC3-2. And in panel L and N, the overexpression of P6 increases autolysosomes and autophagic flux. Then, how can P6 activate autophagy? URK1 is known as autophagy initiation protein. As you can see the panel A, I found out that uracil phosphorylation is dramatically dependent on P62. And also in panel E, P62-induced autophagy is dependent on uracil. Therefore, P62-induced autophagy is mediated by uracil. And I wonder, how can P62 mediate phosphorylation of uracil? Look at the autophagy process. AMPK is upstream of uracil. That complex works in autophagy initiation step. Also, saturated fatty acid-induced mitochondrial dysfunctions that can lead to AMPK activation. So I wonder whether P62 can regulate AMPK-uracil axis. I performed several immunoprecipitation experiments. Please look at the panel A. AMPK-induced uracil phosphorylation is dependent on P62. And in panel B, P62 enhanced uracil AMPK interactions. And in panel C, uracil P62 AMPK, this three complex binding is distinctly increases in response to palmitic acid. So I found out that P62 mediates the uracil phosphorylation by enhancing AMPK-uracil interactions. From now on, for the physiological relevance, I will show you my result of the mice experiment. To set the in vivo approach for nephrid models, mice are fasted followed by refed with high carbohydrate diets that can induce de novo lipogenesis in the liver that causes to physiological lipotoxicity. I was able to see the increase of lipogenic target genes and the number of palmitic acid in this model, accompanied with exacerbated liver injury. Consistent with in vitro findings, I used GFPRC3 transgenic mice and subjected them to refeeding or injecting with adenoviral P62. As you can see in panel A and C, I observed noticeable increase of autophagy in this context. Likewise, this is the same in the adenoviral P62 injected mice in panel E and G. Therefore, I found out that P62 activates autophagy in mouse livers. Then, can P62 protect mouse liver from physiological lipotoxicity? I tried rescue experiments using adenoviral P62 terivane injection in P62 conventional knockout mice. And I found out that reinforcement of P62 ameliorates liver injury through uracil-mediated Kibon-NR pathway in P62 knockout mice under lipotoxicity. Lastly, to identify the clinical significance, I performed experiments using the livers of human nephrid patients. As you can see in panel A, P62 is increased in the livers of nephrid patients compared to normal individuals. Also, uracil phosphorylation induced autophagic Kibon degradation and followed by NRF activation with NRF target genes in nephrid patients. At the same time, oxidative stress-mediated liver injury was unregulated in nephrid patients. Therefore, these findings provide the important insight into the clinical significance for the proposed mechanism. To briefly summarize it, I came to the conclusion that P62 activates NRF via uracil-mediated autophagic Kibon degradation, and P62 can protect mouse liver from lipotoxicity. Therefore, P62 can be a good target to find nephrid. This led to publication for a research article in autophagy. And thanks to everyone who helped my study, and thank you very much for your attention.